Hello and welcome back to the NPTEL course on inverse methods in heat transfer. In the previous portion of this week, we saw what the difference between a forward problem and an inverse problem was. In this video, what I wish to do is to show you with a very simple problem, just as an illustrative example of how an inverse problem solution would actually work. I am not actually going to put in any numbers and show you how this works. I just want to talk about the overall process. So, if you pay attention to the process, what you will notice is that for solving a single inverse problem, you actually need to solve multiple forward problems. So, this is what I call the inverse solution process, and we will see this repeatedly through this course, and I will come back to this also when we come to the machine learning portion. So, this video is purely meant to introduce you to what or how an inverse process could possibly work, and then we will see greater details in the coming weeks. So, here is the example of a direct or a forward problem. Okay. It is a very simple forward problem. You have already solved problems like this during your heat transfer class. So, the problem works in the following fashion, or it is the following problem. You consider a 1D problem and its steady state, and it is a conduction problem within a slab. It is a simple sort of problem which you have seen. So, let us say the left hand side temperature is as given, T0 is 16 degrees centigrade and T at x equal to L is given to be 10 degrees centigrade. So, you are given the temperatures and the left and right end, and the length is given. You are also given the conductivity. So, what you are asked to find out is what are the temperatures at these 6 points. So, suppose we say Ti, which is basically T1, T2 up till T6. What are these 6 temperatures? Okay. So, this is a simple enough problem. You would have already seen this during your heat transfer class. You already know that you can basically say that the temperature is linear, and given these two temperatures, you can basically find out that it is going to be a line going from 16 to 10, and you can easily solve for A and B here. Okay. So, this is a straightforward direct problem. Given the left and right temperatures, find out the temperatures within. Okay. So, this is the forward problem. So, pay attention to this, because I will come back to this when we try to solve the inverse problem. So, here is the inverse problem. The inverse problem is like this. Suppose you are given something else. Instead of giving you the left and right temperatures, suppose I give you measurements used based on thermocouples. So, we are making now, remember what we talked about earlier about making a series of observations. So, we now observe the temperatures at these 6 points, and we ask the opposite question. We ask 2 opposite questions or 3 opposite questions, but essentially 2, which is we do not know what the left and right temperature are. Can we find those out? If we can't find them, we can at least estimate them. Can we at least estimate them within a certain range? Similarly, the question is, what is the heat flux? Okay, now remind yourself of this the actual practical case that I showed you about the re-entry atmospheric re-entry vehicle. You can see that it looks more or less like this, except it is kind of turned on its side. So, if you remember, we had a very similar case where we measured the temperature inside and we wanted to find out what Q is. Okay. So, what was Q given T? It is the same thing here. See, given all these temperatures, can you find out what Q is? Okay. So, this is in some sense related to the practical problem also, but you can also see that it is very close to the forward problem that I just showed you. Okay. Now you might think that this is straightforward, but there is a little bit of a problem which I will show you when I show you the plot of how these measurements look like in practice. So these are actually from something like a practical case, not quite, we didn't measure this actually in the lab, but this is somewhat indicative of what you would see in the actual lab. So now here are the actual temperature measurements plotted. Okay, so these are the x locations. So this is I equal to 1, I equal to 2, etc. You can see that these are the temperature measurements. Okay, notice that they do not lie on a line. As I told you with the ball falling through air, in practice what you are going to see is, you might call it noise, maybe due to noise within the thermocouple, maybe due to measurement error, or maybe due to material inhomogeneity. Okay, so it might be due to other genuinely physical effects that we are not accounting for. But what you notice is these points which indicate the temperatures are actually not perfectly within a straight line. So suppose you choose to make a line through these two and try to predict, sorry about that, suppose you try to put a line through these 2 points and try to predict what T0 and TL are, if that is what we are trying to predict, that will give you one prediction. Or if you try to predict the heat flux, this will give you, this line will give you one prediction. If you draw this line, that will give you some other prediction. So you will see now you have a problem of uniqueness, as is the case with inverse problems. So you do not have any unique solution. You do have solutions, but you do not have a unique solution for either Q or for T0 and TL. All right. So in such a case, how do we actually go about solving a problem? So you see 3 lines here. So the general solution process is like this. So this is what, as I said, I will call the inverse process. Now this supposes something. Suppose we have a, I am going to call it forward model. What is the forward model? The forward model says, if you give me T0 and TL, I can find Ti for you. Okay. Just to show you, here is the forward problem or the direct problem. What did we give here? We gave you T0, we gave you TL, these 2 values were given, and we were trying to find out Ti, okay, temperature at these 6 points. Okay. So that is T0 TL, find Ti. So this means that Ti, all the temperatures are a function of T0 and TL. Okay. So this is what is, we have this model. Okay. How do we have this model? Usually from physics, which we will see a little bit later today. So from the physics of the problem, you actually know that given the left and right temperatures, I can find out what the temperature distribution is going to look like. Okay. So what is the process? The process starts as follows. Step 1, guess for T0 and TL. So what do I mean by that? Guess for T0 and TL. Suppose I guessed T0 is, let us say, 15.8 and TL is approximately, let us say, somewhere around 4.5. Okay, so this is my guess. How did I get this guess? I got them randomly. Okay. I just got lucky that I guessed somewhere close to the actual value right now. But so I can just make some guess 15.8 and 4.5 or 0 and 0, whatever you have. Now, once you guess that, you will say apply forward model to obtain Ti. Okay. What does this mean? Okay. So, what this means is, suppose I guessed these two temperatures, I immediately know from physics, from my forward model, that the temperature at this location, this is the new temperature, okay, so on and so forth. So, this is T6. Now, just in order to ensure that we do not confuse notation, we have the actual temperatures. So, these temperatures are the actual temperatures. This we will call T1, T2, T3, T4, T5, T6. So, this I will call T1, T2, T3, etc. But what about the values that I just obtained? This I am going to call T1 hat. These are from my model, and these are what is in machine learning, this is called ground truth. Okay. These are the actual experimental values. Okay. So, notice this. So, this is the experimental temperature 15.46 for example here, whereas your model based on these bad random guesses of 15.8 and 4.5 gave you some other value which we are going to call T hat. So, I am going to call this T hat. Okay. Now, notice that in general Ti will not be equal to Ti hat. That is, whatever we guess the temperature to be, that is not generally going to match what reality is. Okay. In fact, you can see that reality can never or your model guess is never going to perfectly match reality, because you are only guessing. This is a model with some values, okay, of the temperature, and that is not going to match the real value of temperature ever. Okay, notice these are very different. Okay. So, the values here. So, what do we do? So, the next step is change, or more importantly improve our guess for T0 and TL. Why? To reduce the gap between Ti and Ti hat. So, to reduce the gap between reality and model, we improve our guesses for T0 and TL. So, let us say this was a bad model and you made a new guess. You said, okay, I am going to guess T0 is like 16.2, I am going to guess T0 is 16.2 and TL is something like 14.5. Okay. So, suppose you make that guess, you land up here. So, this is the newer guess. It started here, it ended up here, you still have a gap. Now, suppose you keep on iterating, you know, you go here, you come back here, you come back here, come back here. After some time, you come to some line that looks like it is kind of okay. Okay. It looks like it's kind of okay. How do we decide it's okay? How is it not okay? And how do we actually make sure that we always come towards the answer rather than going further and further away? This we will discuss next week. But for now, roughly the process is make a guess, improve the guess, keep improving till it starts looking like you are fitting your original data fairly well with your model. Okay. So, you continue this process till you are satisfied. Okay. So, effectively you go here and you improve. Now, notice that in this whole process, as you are going back and forth and back and forth, what are you doing? Each time you are applying a forward model. I made a guess, applied a forward model, got some values of t hat. Now, I make another guess with another two values, and that gives me a new guess for the intermediate temperatures. Keep on making it. So, as you can see that entire process involves multiple forward models. So, multiple forward model, I am going to call it runs, okay, as if it is a computer program. So, you take a forward model, let us say you make a guess and a computer program gives you a forward model, get a TI hat, improve, keep on running it multiple times. So, the catch here is each inverse problem solution involves multiple forward problem solutions. Okay. So, without having a forward model, really speaking, you cannot have or you cannot solve an inverse problem. Okay. So, the inverse problem is inverse of the forward problem. So, you actually need a forward model in order to run the inverse problem. Just like with the Neptune orbit case that I discussed, we needed to know Newton's laws of gravity in order to figure out that Neptune was there. You can't randomly guess. It is that model which helps you iterate and come to the final solution. So, what this tells you is in order to solve inverse heat transfer, you actually need forward heat transfer. So, you need some forward heat transfer model. So, that knowledge has to be brought to bear in solving, in fact, multiple times during the solution of a single inverse problem. What we will see in the next couple of videos is a very quick recap of some simple forward heat transfer cases, which we will be using as example toy problem cases through the rest of the course. Thank you.